confidence interval. A confidence interval is an interval estimate with a level of probability attached that the interval was drawn correctly and mu is actually in there. All right. So what you do for a confidence interval, it's a range or interval estimate. But in addition to having this range or interval drawn around X bar, because normally when we do confidence intervals, it's around X bar. So not only are you drawing a range of values around X bar, but you're also specifying a level of confidence, in other words, a level of probability that the parameter is somewhere within that interval. Okay, I'll give you examples, etc. But first, our goal is to keep the confidence high. In other words, we want the probability of being correct. We want that to be high and the size of the interval small. So, a range of 10, okay, like an interval size of 10 would be preferable to an interval size of 20 or 30. But we still want the probability of being correct to remain high. Now, there are 3 commonly used confidence intervals: 68, 95, and 99. That's not to say you couldn't have a 97% confidence interval or a 72% confidence interval, but then everybody would look at you weird. All right? So these are the ones that are the most common. Now, let's look at what 99% confidence interval would say. What it says is that 99 times out of 100, if we were to sample from the population and calculate the interval, that is the range of scores around the sample mean, the interval would have been calculated correctly. It would be large enough that mu is actually within that interval. All right, so let me say that one more time so you don't have to, rewind the tape. If we're using a 99% confidence interval, we are saying that 99 times out of 100, the interval size that we drew around X bar, that we calculated, was drawn correctly such that somewhere in that interval we've captured mu. Okay? And if you were, I'll talk about this in a second. If you were using the 95% confidence interval, all you do is you substitute 95 here. So you say 95 times out of 100. We have drawn the interval correctly. We've calculated it correctly. And somewhere in that range of values, we've captured mu. All right. If it was the 68%, again, it means that, look, if we did this 100 times, all right, sampled and drew a range of values around that sample, if we did this 100 times, 68 times out of 100, we have calculated the interval correctly, and mu is somewhere in that interval. All right, so the way we explain it doesn't change. We just change the number from 68 to 95 to 99. Now, a word of caution. Do not say this or explain a confidence interval this way. If I ask you to explain the 99% confidence interval, do not say, I'm 99% sure that I got it right. Or I'm 95% sure that mu is in this interval somewhere. If you say, I'm sure, 95%, I'm sure, then what you're not doing is conveying to others that you actually calculated the odds. If you just say, I'm sure, that sounds like, well, what did you do? Like, did you dream that this was correct and therefore you're basing it off of that? Did you consult your psychic? Did you ask a famous person's uncle to see what he thinks? All right, so how did you come up with, the I'm sure? So it's very subjective, right? When you say that, I'm sure, that's subjective. We want people to understand that confidence intervals, CIs for short, confidence intervals are actually calculated using formulas. Now, you might think that what you do is you draw a range of values around X bar, right? X bar plus or minus something. And then you estimate the probability using a formula that mu is somewhere in that interval. But it's actually just the opposite. What we do first is we have to decide what are we going to calculate, the 68%, 95, or 99% confidence interval. After we have that, then we use a formula to get the number that's going to be added and subtracted from X bar. I'm going to show you these formulas, and then we're going to go through an example, okay, to make sure that you understand. So, how would we find the 95 or 99% confidence interval for the mean? Right? Those are common. 68% I'll show you later. All right. So, first of all, the formula. Now, this is a helpful formula to know, specifically this one. I'm going to show you in a second. We don't actually ever use this one, but this one will help you to understand what's going on. So it's a definitional formula, which is why I'm going to say that you need to know this, okay? All right, so first of all, let me explain why we don't use this one. X bar plus or minus Z times standard error of the mean, where standard error of the mean, we're using the actual standard error of the mean and not an estimate of the standard error of the mean. In order to use this formula, you need to know what the standard deviation is in the population. Well, how often do we know the standard deviation in the population? And if we were testing entire populations, we wouldn't have to ask, well, are the means different because of sampling error or something else? There is no sampling error if you are testing an entire population. It doesn't exist. You can only have sampling error if you sample. All right? So we don't know standard deviation of the population, and if we did, we would not be asking the questions, is this sampling error or something else? It would automatically be, it's the something else. So we don't use this formula. We then, instead of using standard error of the mean, we use the estimate of the standard error of the mean, S sub X bar. And this formula works fine as long as you have sample sizes greater than 30. As soon as we begin to drop below 30, we have a problem. We can no longer use Z equals 1.96. Now, why are we using 1.96? Well, you might recall from the chapter on Z-scores that imagine you have like this nice normal distribution in front of you here, okay? Remember that? Between plus and minus 1.96, do you remember what the percentage of scores, all Z-scores, between plus and minus 1.96, what percentage of them falls in between those two Z-scores? 95%, right? So 95% of all the Z-scores in the universe and beyond, past, present, future, fall somewhere between plus and minus 1.96. All right? So when we want to find the 95% confidence interval, the mean is going to be smack dab in the middle, and then we want 95% of all the Z-scores around it. That's going to give us the best chance of capturing mu. So we want the middle 95% of the distribution. So we're going to use a Z-score equal to 1.96. All right. Now, so what we're going to do is we're going to take our sample mean, whatever that equals. We're going to minus this answer here. We take our Z-score times S sub X bar, the estimate of SEM. So we multiply these two together and we're going to get an answer, right? So then you go X bar minus this, and that gives you the lower limit for your confidence interval. Then we take the mean and we add this number here, whatever that turned out to be, 1.96 times standard error of the mean, the estimate, and that gives us our upper limit. And then we just write it this way. We say that mu is somewhere between the lower limit and the upper limit, somewhere between. And again, we are not 95% sure that we're right. We say 95 times out of 100, we have drawn this interval correctly, and mu is somewhere within this range of values. Well, of course, there's a 5%, 5 times out of 100, we're going to be wrong about this, right? We've not drawn the interval correctly, and we missed mu. Now, if you were calculating the 99% confidence interval, the only thing that changes is the z-score. So if you want the middle 99% of the curve, you don't use 1.96, you use 2.58. Okay, so you just put 2.58 here, and the rest of the calculation is the same.